Right, so what we're asked to do here is to use the trapezoidal rule with 4 subintervals to find the volume of the solid generated when y equals sine x is rotated about the x-axis between x equals 0.2 and x equals 0.6. All right, a few things to start with here. So, trapezoidal rule. We're using the trapezoidal rule, which in basic terms is, in this case, I'll put it down for an area first. It's an approximation of our area, which is our height over 2 plus the first function value plus 2 times each of the middle function values plus the last function value. I'll explain exactly what this means. So what we're doing here is our height is the distance between each of our shapes, and as the name suggests, the trapezoidal rule actually works by taking some curve. In this case we've got sine x, which is up here, and taking between two values, I've just picked two random values there, and turning that into a number of different trapeziums. Now it's an approximation because it can't actually follow that curve perfectly. It actually forms straight lines there. Now by adding together those 4 trapeziums, we get an approximation of the area. The more trapeziums we have for the same length, the more accurate our answer is. But in this case it's a volume, and it works in a very similar way. So that's how our trapezoidal rule works to start with. Now there's 4 subintervals here. The 4 subintervals is a key idea. Now I've actually drawn how many subintervals there? 1, 2, 3, 4. 4 trapeziums, but in fact what you'll notice is I've got 5 yellow lines, which is why we have this down here where we have the first and the last, and then twice the middle. Well, that's because if I go and just using our basic formula for the area of a trapezium, if I went and found the area for each of these trapeziums and added them together, well, what you'd find is that I'd end up using this value here and this value here only once, but each of the ones in the middle I'm going to use twice. So that's where our rule basically comes from. And the only difference here is that because we are finding a volume, or the approximation, again, it's an approximation of our volume is h over 2 and each of the squares of those. So it's the first squared plus twice the middle values squared plus the last function value squared. I'll show you a reasonable way to do this in a second, but that's our general idea. Okay. Now we could go find our volume by doing an integral straight away, not an approximation. It's not what we're asked to do, but we could use that to check. So we could go volume equals pi of, well, y is sine x, so we'd use y squared, which is sine squared x, dx between 0.6 and 0.2. Now, depending on the level of course you're doing, that's a harder integral. So we may not be able to do that. That's why we would use an approximation. Once we've done our approximation, I'll show you what the answer for that is using our exact method. But for now, well, let's proceed with our approximation. Okay, so we know we've got these values here. We've got our x equals, I'm going to have our x values and then our y values. So 0.2 is our first value and 0.6 is our last value. Now, as I said, it's 4 subintervals, which means there's got to be 4 lengths, which is actually 5 values. So think about it, if you look at the fingers on your hand, well, you have 5 fingers, but there's 4 gaps between those fingers. So there's actually 4 intervals between your fingers. There needs to be a 5th finger to form that 4th interval. So if you are using 4 intervals, 4 subintervals, then you're going to be using 5 values. Now if it says to use 4 values, that's different. That's used 4 function values and you split that into 4 parts as opposed to 5 here. So what we recognise, and it works out quite nicely, is that if we look how far we go between our 0.2 and our 0.6, that's 0.4. So we're actually going to be able to have them at nice 0.1 increases. And that's important as well, because straight away our height is the difference between our x values, which is 0.1. That's important for us to note, because that goes into our formula. Now, we could jump straight to our calculator here and go, well, that's going to be the sine of 0.2, the sine of 0.3, and so on. I don't think we need to go and put that into our calculator because that's going to be an approximation. And then just like we saw in the previous slide, well, we need to square those anyway. So I think it's probably a better idea for us to use our calculator here, because then there's one less calculation to perform. So I think we can go and put in, I'm simply going to put these in and going to know that's sine squared of 0.2. Now, something that's important to understand is this is what we are finding. So if y equals sine of 0.2, that's my first y value. The square of that, there's a couple of ways we could write that. Sine of 0.2 squared, which is sine of 0.2 multiplied by the sine of 0.2. It's not the sine of 0.2 squared. So we're not squaring the 0.2, we're squaring the sine of 0.2. And that's typically written in this fashion here. If you're not familiar with that notation, I'm sure many of you are, and you can just ignore that. So we're going to need to use our calculator here because these are not nice exact values. So this one will be sine squared of 0.3 and sine squared 0.4, sine squared of 0.5 and sine squared of 0.6. So we're going to go add those together. Now remember, we are going to have to double the sum of those three. So I would simply go into your calculator and be doing this now. And then of course we're going to have our substitution here, which we're going to need to use our calculator for. So our volume is going to be approximately equal to my height, 0.1 over 2, outside of, well, sine squared 0.2 plus, well, 2 of sine squared 0.3 plus sine squared 0.4 plus sine squared of 0.5 plus then our sine squared 0.6. Now again, because these values in here contribute to two different trapeziums, once we graph that, what we end up with is doubling those ones and adding just one lot of the first and the last. If you put all that into your calculator, remember that if you're writing down each of the values individually, use a number of decimal places. What we end up with is 0.064797, which I'm going to call 0.0648 cubic units. Now remember, that is an approximation. It's not exact. It's an approximation of those of that volume there. Now I mentioned earlier that we could do this by doing an integral. That might be too difficult for the course that you might be doing, but I will show you it anyway, just to confirm that our answer is right. So we could set it up this way. We could say between 0.6 and 0.2. Now, of course, we find a volume by finding the pi of y squared. So we said pi of y, or y is sine x, so y squared is sine squared x with respect to x, because we're going around the x-axis. Now that becomes the primitive. Actually, we can rewrite that sine squared x by manipulating it as it becomes 1 minus cos 2x on 2 dx, which we can integrate using our standard techniques, which becomes x on 2 minus sine 2x on 4, and of course still between 0.6 and 0.2. Now if you go substitute into that, you do end up with our value there Here we end up with 0.20214, which is 0.202 cubic units to 3 significant figures. And it has just occurred to me that on my previous slide I've actually made an error. The error is that I have not multiplied the whole thing by pi. So in fact what this slide should read, my apologies, is I have to just multiply this number here by pi, of course, because we're finding a volume, which means our answer is simply that number multiplied by pi, which does end up becoming our same value, approximately 0.2035, so I'm going to go 204 cubic units to 3 significant figures. Now again, it is an approximation, so don't expect the exact same answer. You should expect a slight variation. As I said, the more divisions we use, the more intervals we use, the more accurate it will become. If we were to do this with one interval, we would find that we would be quite inaccurate. But if we were to use, say, 20, we would become very accurate. But obviously that's a lot more effort. So here, our answer of 0.204 is quite accurate to the exact value of the integral. Apologies for the error. That in fact is our correct answer there, not what appears on the second slide. And we have our answer for using the trapezoidal rule to find a volume. So the main thing I would say in answering this type of question, I would write out all your values in this case, as I've done up here. Make sure you note your height. Your height is not the difference between 0.2 and 0.6. Your height is that difference dividing by how many intervals you are using. So in this case, our gap there is 0.4, using 4 intervals. So we divide it by 4 and get a height of 0.1, which comes down to here in our formula. Okay, so that would be the main takeaway point. And then of course we've got just one lot of our first and last values, plus twice the sum of all those middle terms. Okay.